Whatever the number of turns here, which acts like a current loop, which means the current is flowing through the coil, and that can be detected with the help of galvanometer. So the SI unit of magnetic flux is Weber, which is denoted by WB. So when it moves to its left side, the area of the rectangular loop decreases. So when the area of the rectangular loop decreases, the movement induces a current in the setup. Hello everyone, welcome to first session of Chapter 6 Electromagnetic Induction. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. What is electromagnetic induction? What is necessary to study about this topic? We have studied about the magnetism and matter. We have studied about the current electricity. We have studied about the moving charges and magnetism and the phenomena, the various phenomena involved in all these concepts in our last previous chapters. So in this chapter, we are going to study more about the generation of electricity with the help of varying magnetic fields. By varying the magnetic field with the help of magnetism or with the help of magnets, how can the electric field be generated is what we are going to study in this lesson. So the phenomenon of generation of electric field due to a varying magnetic field is called as electromagnetic induction. Basically, electricity can be generated by the help of induced magnetic properties is what electromagnetic induction. Let us begin with the first topic of the chapter, that is coil magnet experiment performed by a scientist called Faraday. So what was his observation in discovering the electromagnetic induction with the help of coil magnet experiment? So he performs various experiments like coil magnet experiment, coil experiment to discover the electromagnetic induction. And also he gave some observations theoretically by performing these experiments. The experiment name says coil magnet experiment, which means we have a coil in the setup. I'll call it as C1. Say for example, this coil has n number of turns. So it has number of turns and the current is flowing in a coil, and this current is detected with the help of galvanometer. Now, it's a coil magnet experiment. We have a coil and it has a magnet as well. So, I have considered a bar magnet with two poles, that is north and south poles. So, we have used galvanometer here because we know that the galvanometer is a device basically used to detect current in a circuit. So, whatever the number of turns here, which acts like a current loop, which means the current is flowing through the coil, and that can be detected with the help of galvanometer. Now, I have a magnet. So, Faraday observed that when the magnet is inserted inside the coil, he was observing a deflection in a galvanometer. The first observation is the magnetic field generated with the help of a magnet and a coil. So, we know that the magnetic fields, when it is denser, which means the field is more, or the intensity of the magnetic field is more in this region. He observed that when the magnet is brought near the coil, the galvanometer shows a deflection. So, he observed that whenever the coil and the magnet are in relative motion, there was a deflection in the galvanometer. And the deflection remains in the galvanometer only when the coil and the magnet are in relative motion. He also observed that as faster the magnet moves inside the coil, the galvanometer deflection was more and more. If the magnet is brought near to the coil, due to the magnetic field intensity, the current flow is more inside the coil, and hence the deflection in the galvanometer is also greater. Suppose if the magnet is brought far away from the coil, then the deflection was reducing, which means the deflection goes in opposite direction. So from this experiment, we can conclude that the relative motion between the coil and magnet generates EMF in a coil. So this was the basic experiment conducted by Faraday in discovering the electromagnetic induction. With the help of magnet, the current was generated. First observation, and hence he concluded that the magnetic field can contribute in the generation of electric field. He also used two coils, that is coil-coil experiment, in explaining the electromagnetic induction, and gave his theoretical observations, which again helps in understanding electromagnetic induction property clearly. So Faraday conducted these two experiments to explain electromagnetic induction. So let's know about magnetic flux now. What is magnetic flux? We all have an idea about electric flux, that is number of electric field lines passing through a surface. Similarly, magnetic flux is nothing but the magnetic field lines passing through the surface, and it is given by phi b. Since it is magnetic flux, B stands for magnetism, and so it is phi is flux. So magnetic flux is equal to B dot A, which means the number of magnetic field lines crossing through the area. Since it is a dot product between B and A, it can be written as BA cos theta, where B is magnetic field, A is area vector. And what is theta? Theta is nothing but the angle between the direction of magnetic field and the area vector. So the SI unit of magnetic flux is Weber, which is denoted by WB. Let's know about the Faraday's laws of electromagnetic induction. We might have all studied about this in our high school. So Faraday concluded his observations with certain laws. We will call it as Faraday's laws of electromagnetic induction. So what is the first law states? So it says that whenever the magnetic flux passing through a circuit changes, an EMF is induced in it, which was concluded by his coil-coil experiment. So whenever the magnetic field lines passing through a surface changes, EMF gets induced in it. So the induced EMF lasts as long as the change in magnetic flux continues. So it will last till the magnetic flux changes continuously. What is the second law of Faraday? The second law states that the magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux throughout the circuit, which means the magnitude of induced EMF, that is E, is equal to rate of change of magnetic flux in a circuit, where E is induced EMF, d phi b divided by dt is nothing but the rate of change of magnetic flux. So these are the two laws of Faraday in explaining the electromagnetic induction. So our next topic is Lenz's law, which is a very important topic in electromagnetic induction. It states that the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. Which means the significance of the Lenz's law is to give the polarity of EMF, or it also says about the conservation of energy. So our next important topic is motional EMF. What is the meaning of motional EMF? So the EMF induced in a conductor moving in a plane perpendicular to magnetic field is called as motional EMF. Here we have a magnetic field. So if a conductor, or if the EMF is induced in a conductor moving in a plane perpendicular to magnetic field, we will call it as motional EMF. To prove the expression for this motional EMF, we have considered a rectangular conductor here, which is P, Q, R and S. So here you can observe PQ is free to move in a uniform magnetic field. I can move this way or that way, so it can be moved freely. PQ faces are such that it is arranged, they can move freely in a uniform magnetic field. So here P, Q, R and S is a closed circuit. So let us say that the rod PQ is moving to its left side. We have shown it with an arrow mark. It is moving towards its left side at constant velocity V. So when it moves to its left side, the area of the rectangular loop decreases. So when the area of the rectangular loop decreases, the movement induces a current in the setup. Here, the number of magnetic field lines passes through the surface, and the magnetic flux, that is nothing but phi b, which can be given by BA cos theta. We have learnt it in the last slide. So here, since they are moving in the parallel direction, theta value is 0. So what is cos 0? It is 1. So we get B into A. But A is nothing but the area, which can be written as length into x. So x is nothing but the distance moved, and L is this dimension. As the rod PQ is moving with the velocity to its left side, so the x component is changing with time, and we can write it as B is equal to minus dx by dt. So that is nothing but velocity, which is equal to distance divided by time, or the displacement divided by time. So the rate of change of flux will induce an EMF, and it is given by E is equal to minus d phi b divided by dt. What is phi b? It is nothing but B into L into x. So we got B into L into x, substituting the same, divided by dt, or we can write it as BL into dx divided by dt with negative sign. So what is dx divided by dt? It is nothing but velocity. So minus V we can substitute. Here I have minus B into L into minus B we can substitute, which is nothing but plus B into L into V. So E is equal to BLV, and it is called as the motional EMF. So in this session we have learnt about the basic concepts of electromagnetic induction and the contribution of Faraday in understanding the topic electromagnetic induction. We have learnt about various definitions. In the upcoming sessions, let us learn more about the chapter called electromagnetic induction. Until then, keep learning all of you. See you all in the next session. Thank you.